Hey everyone, I recently interviewed Arvind Neelakantan from OpenAI about the new OpenAI Embeddings API on the Weaviate Podcast. So firstly, thanks so much to Weaviate CEO Bob Van Light for putting this together. I really enjoyed chatting with Arvind and it was a lot of fun to go through these different topics. So with respect to all these different topics that were covered in the podcast, the purpose of this video is to break down this list of the chapter topics in the podcast description just to give an overview about all the different things that are going on with text embeddings, code embeddings, deep learning for code, different things about self-supervised learning, ideas like data preprocessing for this embeddings API, and a few different things that were covered in the subject of this podcast about the OpenAI Embeddings API. So first things first, OpenAI has released a new Embeddings API. This has been such an exciting direction in, say, the business category of this deep learning research, as we've seen things like the GPT-3 model as an API, and this general category of deep learning models being utilized as paid APIs and building out that kind of business around deep learning. And it's really interesting because generally you would need to, say, fine-tune your model for your specific domain and have a specific statistical model for your domain, whatever you would need a parametric model for inference for. But the GPT-3 model has been able to show that if you give it these input-output demonstrations, what they call few-shot learning, but just in the input without any actual gradient updates, it's able to perform a surprising range of tasks. And this generality is what's pioneering this new flexibility and this new offering of model as an API. And so this is kind of a similar target with the embeddings API, where they're targeting trying to embed any kind of text, any kind of code, and enable this kind of general embeddings for all kinds of data domains. And that's kind of the flexibility that's powering this idea of deep learning model as an API. And there are some other approaches around this. There's also the Hugging Face Infinity, where they help you deploy your transformer models and optimize latency. And so this is another way of looking at this idea of how we're going to be putting these models into APIs and accessing them. But the embeddings API, the idea of having kind of offloading the model training costs and research and all that kind of idea into OpenAI, is a pretty interesting idea in my view of these things. So to begin things, you see the pricing of things, and I think the really interesting thing is you see how it's tiered, and you might not quite need the Da Vinci model type, the large GPT-3 175 billion parameter version with the, in this case of the embeddings, probably what you care about also is the resulting size of the embedding dimensions and this kind of thing. So you see the differences in prices. This is a really cool thing. You see our tokenizer tool to get an idea of how your input text maps to tokens. You can click it, you can write some text and see how many tokens you're looking at if you want to calculate, how much this is going to cost you to run the API and get the embedding. So generally what embeddings are, if you're still on that detail of it, this is a way of forming vector representations of unstructured data like text data or code data is what we're looking at in this particular paper, in this particular latest advancement of the research. But soon it will be all kinds of things like multimodal learning. You could have image text alignment spaces, like you have the clip embeddings are already something that exists and will probably be integrated with this. And then, maybe you could form vector representations for structured tabular data, graph structured data. It's really, an emerging area of research with forming these embeddings, and I still think there's a ton of more opportunities to explore it and continue to improve it. But what you have in the end is you have these embeddings where you can, say, cluster them, do nearest neighbor search, and that's the point of Weaviate. Weaviate is a vector search database where you put these vectors into your databases alongside your original data schema, and you have full create, read, update, delete, CRUD support with this vector database engine. You have the vector indexes that facilitate doing this at a very large scale. So if you have, say, 1 billion of these vectors, you don't want to be doing the nearest neighbor dot products with all of these vectors. So Weaviate implements the HNSW algorithm, which is one of these techniques to use this centroid clustering, small world graphs, that kind of really cool research ideas for facilitating nearest neighbor optimization. And there's all sorts of other things with Weaviate that I'm not going to get into too much in this video, things like the GraphQL API, the way you can easily stack on modules if you want to decompose your tasks into retrieve then read, and all sorts of other cool things. But so anyways, here's the blog post if you want to get a quick sense of what the OpenAI Embeddings API is before going through this podcast or before continuing to the chapters in this podcast. So quickly before breaking down the chapters in the latest podcast with Arvind Neelakantan from OpenAI about the OpenAI Embeddings API, please check out the Semi Technologies and Weaviate Vector Search Engine YouTube channel. We're working on developing this podcast. We have all sorts of guests have been on so far, and we have quite the queue of upcoming guests. So please subscribe for more content about vector search, different use cases of deep learning for search, and all sorts of cool ideas. So here's the list of the different topics that were covered in the latest Weaviate podcast with Arvind Neelakantan. The first half of this is mostly about embeddings, contrastive learning, different ideas of retrieve and read, say label embeddings for classification. I think this is a really creative idea that we saw with, say, the clip model, where you classify images by having the embedding similarity between text prompts like this is an image of a cat, this is an image of a dog, that kind of thing, for having a label embeddings of the text sequence that would describe a classification label. And anyway, so the first half are general ideas around embeddings, and then we get into deep learning for code. Deep learning for code is so exciting. Personally, I've done some work on this with Keros Burt, trying to language model Keros, and it was so exciting to talk to Arvind about codecs and the super level of this, and understand how, say, code search and, say, retrieve and read, as we mentioned, can help all sorts of different tasks, can help with the codex model, and how search and codex is such an exciting advancement in code generation. And I think this will just supercharge developer productivity. As we talked about open source project support, helping people answer questions about how to use new projects that might not have fully fledged documentation or debugging help with Stack Overflow yet. This kind of idea of code search and code generation, I think, is one of the most powerful emerging ideas out there. So really excited about getting into the second half of this podcast as well, in addition to the beginning about this general concept of embeddings APIs and the latest advances in forming embeddings. So we began with the basic introduction question of what's new with the OpenAI Embeddings API and what is the basic story. Then we got into generally what's new in text embeddings and, say, self-supervised learning. This new contrastive learning law is not brand new, but it's been adopted and used more frequently with, say, things like SimClear, MoCo. We have all sorts of things like bootstrap your own latent, data to vec is probably the most recent one in my mind, but there's been all sorts of different research on self-supervised learning with this objective where you have a similarity scoring on the denominator of a fraction for the normalization of this loss, and then on the denominator you have the distance with a large batch of, say, in batch negatives or something like that. The idea of contrastive learning where you have this representation alignment and then you normalize it by having the distance with all the negative pairs. So that contrastive loss idea generally, and all sorts of advances in self-supervised learning, just like the way to scrape the internet and have these kind of noisily labeled positive pairs, and how that's kind of scaling to produce new advances in all sorts of embeddings. And text recently has seen more and more focus with this kind of research applied to that data domain. So then we got into this topic that is one of my favorite things to talk about on the Weaviate podcast, which is this idea of one model for all domains. As we mentioned earlier, say this idea of a deep learning model as an API suggests that this model can perform on all data domains. And to me, that's an incredibly interesting idea, that you don't need to fine tune it. You don't need to adapt it to a particular data distribution or a particular domain. So say you train GPT-3 on all of internet text, but now you only really care about using it for parsing biomedical scientific papers. Do you need to fine tune it, or is it going to be able to just perform and produce useful embeddings for biomedical papers, even though it's been trained on, say, the entire internet? And I think that's one of the most interesting kind of aspects of this, is seeing whether you need to adapt these models or seeing if they can work off the shelf for all sorts of different data domains. Next up is one of the most important, say, nuggets to take away from this podcast, and that's the importance of data preprocessing for the Embeddings API and some different ideas around how to preprocess data for these kinds of APIs. So first of which, I was inspired to ask Arvind this question because I saw some comment around the internet around talking about how to use this around not including new lines in your text representation. So this is a very interesting idea around adding structure to unstructured text or code data. So say in text you have new lines to, say, signal a paragraph break, or you might even have the HTML tags. And this is one of the most exciting recent ideas in language modeling text. This HTLM model from Facebook Research, it's hypertext language model, where they include the HTML tags to have that kind of structure in the text. So this idea about how do you preprocess your text data, or I think code data, makes it even more interesting, because you say you need to have, the new line in code is signals something. When you say have, for X in range, whatever, and then you have the colon, you're signaling a control block with the way that you're doing new lines and tabbing it. So I think it's kind of important to think about how you're preprocessing that kind of data. But Arvind's dream for this is to just have one left to right sequence. And I think that's extremely interesting. just generally, I think this topic of how we add structure to this is interesting. So I really like this topic particularly, and I hope that listeners of this take away something interesting about thinking about how to pre-process the data for different model inference and different, just having a kind of a standardized way of looking at different text sequences or code sequences. So from there, we talked about the topic of large embedding vectors. And this is another really interesting topic. This is the idea about, say, the largest GPT-3 fine-tuned with contrastive learning API, in this embeddings API, produces 12,000 dimensional vectors. And that helps with, you see as they look at the evaluation, that the larger vectors perform better. But it's very interesting because as you have these larger vectors, they're more expensive to, say, put into something like the HNSW algorithm, or if you're doing, say, just brute force nearest neighbor, having the larger vectors is going to make that take a longer time. So I think it's very interesting to think about large embedding vectors generally. So in the paper Barlow twins, they scaled up the size of the contrastive image models up to, say, 16,000 dimensions, and they show this up and to the right improvement as they continue like doubling the size of the output embedding vectors. Something that we've explored with Weaviate is binary passage retrieval. This is where you have a continuous relaxation with the tanh activation function to put gradients through the binarization of, say, going from these high-dimensional continuous vectors into their 1, 0, 0, 0, 1, 0 counterparts with the binary representation, so that you can have that Hamming distance and facilitate the nearest neighbor search by having that representation of the large continuous vector with the still large but binary representation of each individual slot on the vector. And that kind of idea, you could say, think about doing some kind of reduction of the size. I think that's the idea of product quantization and things like face, and generally, say, having a PCA of the embedding vector. That kind of, I don't think that idea is really working as well as binary passage retrieval, but that's something else to think about. Next up, we have the evaluation of embeddings, and this is maybe where the controversy of this comes in, and also, say, this topic of one model for all domains. So as Arvind describes, they evaluate these embeddings on a massive set of databases, and you, say, have text search databases like, say, MS Marco, you have question answering datasets like Trivia, QA, natural questions, that kind of thing. Then you also have, say, sentiment classification, where you put the linear probe on the embeddings, or you have, say, natural language inference, all sorts of data sets for evaluating the quality of these embeddings. So it's pretty interesting. You also have the BEIR benchmark. That's probably one of the most important ones to be looking at with respect to these information retrieval benchmarks. There's also knowledge-intensive language tasks, the KILT benchmark, where you have a snapshot of Wikipedia, and then from Wikipedia you do the different tasks. And we have a Wikipedia demonstration on Weaviate if you're curious about getting started with what that might look like right away. But anyway, so it's a general topic of how do you evaluate these embeddings, generally the scope of model as an API, one model for all domains. I think even though it's performing pretty flexibly for these out-of-distribution domains, and there's other papers, a recent paper review on Henry AI Labs was robust fine-tuning the weight space ensembling technique, where what they're doing is they take the pre-trained clip model and they show how it has all this zero-shot flexibility for, say it can adapt to sketch images or adversarially corrupted images. Just generally, if you have an image classifier and you apply data augmentation to the test set, it's probably going to completely destroy the image classifier. So these pre-trained models like CLIP, they're more robust. They have more zero-shot flexibility, more robustness. But then as you fine-tune them, they get better at the in-domain thing, but they lose the zero-shot flexibility. So weight space ensembling is a technique to combine those two models and achieve that balance, the trade-off, say, Pareto frontier between zero-shot flexibility and then your fine-tuned downstream accuracy. So generally, evaluation of embeddings, one model for all domains, this is going to be a topic that I don't think is going away for the upcoming few months at least, and it's something that will keep coming up on the Weaviate podcast. Next up, we talked about what I think is the most important trend in the performance of these deep learning models, and that's the decomposition of these different tasks into retrieve and then read components. So mostly when we think of retrieve then read, the retrieval allows us to have this interpretability in the information that the reading model is using to make the current inference or the current prediction for the task. And it also allows us to update that information. So say that information becomes outdated, it's replaced, it's something that's time sensitive, or if we realize that there are all sorts of biases and negative things in the data that we don't want to be in there, we can update that, and then we have this separation of retrieval and then reading compared to end-to-end storing the entire data set in the parameters of one model. The retrieval lets us swipe that out and have that easier updating, and also further just facilitates not needing these massive models because of the decomposition, and the parametric capacity is of needing to store the data set in the parameters is reduced. So Retrieve then Read has seen very interesting advances in, say, WebGPT, DeepMind Retro. Facebook AI has internet augmented dialogue generation. This idea of having a retrieval step and then a reader step, or just generally having, say, a language model that, like the Lambda model from Google research, it accesses a factual information source, it accesses a calculator, it accesses these kind of things. Like, it has that kind of decomposition where it can access external components, similarly to, say, humans, that kind of thing, where you can have these auxiliary information sources and auxiliary kind of capabilities of the model that aren't just in one parametric model. So that's a very interesting topic of using these embeddings APIs to retrieve context from your data for your current downstream task. So say you're training a question answering system and you want to retrieve relevant context for the current inference, you can use the OpenAI Embeddings API to do that retrieval and then supplement your question answering model. So regarding retrieve then read, this essentially turns the problem into a k-nearest neighbor regression, where you're using the k-nearest neighbors from your training set to supplement the current inference, and then obviously you still have like a nonlinear regression where you're going to put at least, say, 6 layers of transformers, so to say, on that reader component, but you still have that kind of k-nearest neighbor regression in terms of thinking about this from like, what kind of machine learning problem does this look like? So another interesting idea that Arvind brought up is the idea of label embeddings for classification. So say you have, in the OpenAI clip model, you have the image and then you have text descriptions of the label. So compared to the one-hot vector strategy for representing class labels, you have this is an image of a cat, this is an image of a dog, this is an image of a frog, and then the maximum dot product vector similarity is used to make the classification. So I think that's another really interesting topic. Then we got into the super exciting topic of prompting. So as mentioned earlier with the idea of GPT-3 as an API and what's kind of enabling it to be one model for all domains, the prompting is where you add extra context to the input, and these large models have more capacity than we understand, and the contextual representations are so powerful that adding this additional information in the input kind of, filters it to guide it in that kind of task space. If you think about all the kind of crazy high dimensional things of like manifolds and all that crazy stuff, but this idea of prompting helps guide it and shape it into the direction of your task, into your data domain and all that kind of thing. So the first question I asked is, what about the use of prompting in embeddings? So a recent paper that was covered on one of the AI Weekly Update videos on Henry AI Labs was this idea of prompt BERT, where they use different prompts, these templates, to get better embeddings for query document matching. So they say, I have a query about X being the original input, and let's say like mask or whatever. Like you have some kind of template that guides how to form the embedding for the given query. And the other thing as we then get into prompt search is this kind of provides like a free ensemble learning. And I think ensemble techniques are one of the most interesting and powerful ways to just boost a machine learning model by having that kind of functional diversity in the space. So prompt search, you could give it, say, 5 different prompts to get 5 different embeddings. And as we've seen, say, concatenations of sparse lexical retrievers like TF-IDF BM25 with dense SBERT, you could similarly sample 5 different prompts and have 5 different dense vectors, average them out, have some kind of parametric layer on that if you like, and you can have that kind of idea to facilitate prompting for embeddings. But then there's kind of another idea that we talked about, which is the search for prompts for the downstream tasks. So most of the time when we're talking about search and retrieve then read pipelines, we're talking about retrieving factually correct information to avoid this hallucination problem and make factually correct outputs. But you could also search for prompts, and this is an interesting idea. There's all sorts of strategies for searching for these, say, discrete prompts where you can look at them and say, okay, I have a sense of what this prompt does, compared to, say, putting the prompt in the continuous space and optimizing it with gradients is another strategy of prompt tuning. But generally thinking about, say, using Weaviate and using the nearest neighbor functionalities for finding the optimal prompts for, say, GPT-3 or something like that. Now we're starting to get into the topic of deep learning for code, which to me is one of the most exciting areas of deep learning in general. So we start off with this idea of multimodal text and code. So currently what we have is the text embeddings for the new paper are still unimodal. We have the adjacent sentences are used as the positive pairs, and then you have a large batch of sentences to get the negatives for that denominator term in contrastive learning. But the code representations are multimodal, where the text docstring is the one half of the positive, and then the implementation of the function, that's the other half of the positive pairings. So docstring function implementation, that's the positive pair. for doing this kind of contrastive representation alignment. So it's kind of obvious what text adds to code. So I was curious maybe what code might add to text. So we've seen a lot of recent papers like reasoning like program executors and all sorts of things like turning tables that show how to parse tables into like language modeling data. So what might turning code into language modeling data, what might that add to text embeddings? Maybe this kind of, esoteric idea of reasoning, maybe that is achieved by modeling code, and modeling that kind of symbolic program execution could add to text codings. So the next thing we talked about is a super exciting topic of deep learning for code. Obviously, OpenAI Codex, GitHub Copilot, one of the most exciting examples of this out there. And personally, I've worked on this a little bit with the Keras-BERT project, so I love talking about this, and I loved hearing about Arvind's thinking about this direction. The next topic I think is a very important practical detail for these code generation models. So the current practice, and is documented in DeepMind's latest AlphaCode model, is currently they have a massive amount of oversampling from the generative model to get it to pass these, say, competitive programming tests. So what this means is in OpenAI Codex, they call this repeated sampling, where they keep sampling from these potential generations to get something to finally produce to the user to submit to the competitive programming contest. So from the high level basics, what you have is when you have these language models that fill in this mask token at the end of a sequence, so say you have embedding architecture bottlenecks, and then here you have mask, and then whatever it predicts for that mask, you would then put another mask after it, and you keep doing that so you generate these trees of potential decodings. So these trees are weighted by the probability density that the language model put on that word at each individual time step or each potential traversal through that tree. So you could generate, in the case of AlphaCode, I think it's even millions that you generate by really expanding that tree to a heavy degree, especially with things like byte pair encoding, where the tokens, they don't even generate whole words. Parts of I'm not sure if that's really how tree decoding works, but you can just think of kind of like the flexibility of how much you can traverse that tree decoding space to generate many potential candidates for the code generation. So a really interesting idea is semantic duplicate filtering, and how that is enabled by these semantic embeddings and semantic search. So by having, so say you are writing a function for the Fibonacci sequence, you could title the function in two different ways, like def fib n or def Fibonacci sequence n, that kind of thing. And you could also then you name the variables different things, add comments maybe. There are in the same kind of idea of nearest neighbor search and fuzzy semantic similarity, there are different ways to write the same function. So in code forces and a lot of these competitive programming problems, you can just run the input-output because it doesn't take too long. But as I've been thinking a lot about Keras-BERT and language models that write deep learning code, we can't just test these things because they take a long time to test. So maybe what we need is this kind of code search and these embeddings, and Weaviate in their GraphQL API has a merge function where you can merge together things that have too much semantic similarity to filter that out and only get unique code snippets for this kind of sampling to the actual compiler. So then to kind of round out the podcast, we talked about how code search can enable open source project support, how we can use these different tools to help people search for code snippets, get help for debugging errors with newer projects. And I also really like the idea that Arvind brought up of multilingual text-to-code search. I think that's another really exciting component of this. Then we talked about compilers and deep learning for code. The general having that kind of correctness with the compiler, I think, is something that fundamentally distinguishes code and text representation learning and just kind of supervised learning, that kind of thing, where you get your reward signal. Because in compilers and in code, it's correct or it's not correct, kind of, compared to like text recommendation, where say you're recommending a scientific paper and there's a lot of fuzziness with respect to how you really evaluate that. So then we talked about latent knowledge representations. I'm curious about, say, the discrete bottlenecks in the middle of these networks, and Arvind has done some research on vector quantization and the vector quantization variational autoencoders, and these kinds of ideas are taking off as huge advances in image generation. So I was curious what he thinks about this in the scope of these neural language models. Then we talked about embedding architecture bottlenecks. This is another extremely interesting topic where say you have the Siamese BERT And the way that produces a vector is you have an average pooling along the sequence axis to produce the vector embedding, compared to just applying a masking on the isomorphic transformer. So they call these transformers isomorphic because they don't compress the sequence. So say you pass in a 512 length sequence, it will also be 512 by the embedding dimension when it comes out of the output of the transformer. And then you index it with this masking to make the prediction on the mask spot, or say you have the CLS token, that kind of idea, compared to something like Siamese BERT, where you do the sequence pooling, or say funnel transformer, where you compress it with sequence pooling, skip connection, that kind of thing. So I was curious what Arvind thinks about these embedding architecture bottlenecks. And I think the takeaway was Arvind believes that this is useful, like say UNet style vector compression is useful for domains like perception with a high signal to noise ratio or low signal to noise ratio, compared to text that is kind of the other way around. And you need the embedding vectors, and you need all the parallel processing to maximize that kind of representation. Thank you so much for watching the latest overview of the Weaviate Podcast with Arvind Neelakantan from OpenAI about the new OpenAI Embeddings API. I know this is a ton of different topics, so I think in this case it might be better to watch the podcast compared to this particular video of just kind of running through different things. Maybe the more conversational style will help to make these things more clear. So thank you so much for watching, and please subscribe to Semi Technologies on YouTube for the upcoming episodes of the Weaviate Podcast, which we're really hoping to develop and deliver this kind of content about deep learning for search and all the different aspects of it, from the embeddings API to the different use cases to other tools like Haystack for connecting these retrieved and read pipelines, from interviews with members of the Weaviate team, from Bob Van Light and Eddie and Dillacker is what's currently up on the Weaviate Podcast, and adding more team members soon, and then more applications like the Kenius academic search system, all sorts of cool things which we're looking to expand on in the Weaviate Podcast. So thanks so much for watching, and also please subscribe to Henry AI Labs for more deep learning and AI videos.